Project 3 by Dylan, Noah, and Christopher. So we have the vacancy general equation here. It's N is the number of atomic sites, QV is the activation energy, KB is the Boltzmann constant, and T is the temperature in Kelvin. So the number of vacancies in zinc, we take the equation here, we plug in the variables, we find that the number of vacancies is 8.0 times 10 to the fifth vacancy sites, and then the number of vacancies in copper, we do the same equation, and we find that the number of vacancies is 3.93 times 10 to the 16th vacancy sites.
Okay, so next up we have Frenkel and Schottky defects. This is a picture of what they actually look like. Frenkel defects is when you have two cations like coming together and to an interstitial point and create a vacancy there. Schottky defects are when you have a cation, anion, both missing, so it still remains charge neutrality, but you have this whole vacancy here. And to find Schottky and Frenkel defects, the equation is pretty similar. It is pretty similar to the same thing as vacancy sites, but you have number of atomic sites times e to the negative activation energy of Frenkel and Schottky defects divided by 2 kVt specifically. And then to find N, take the density of your material times Avogadro's number divided by molar mass. And yeah. So the equations for both Schottky and Frenkel are basically, they're the same thing. You just have to find the specific activation energy for a Frenkel defect and that for a Schottky defect of your material. So here we have it for gallium and arsenic. Find the given values, density of both of them and the molar masses. The specific energy for a Frenkel defect in gallium was 4.8 eV, and then the number of Frenkel defects is really small. It's 1.31 times 10 to the negative 18 per centimeter cubed. So there really isn't any at room temperature. And then for arsenic, same thing, find all the values. It has an activation energy for Frenkel defect at 3.7 eV about, and once again, it's very low with 2.39 times 10 to the negative 9. Now moving on to Schottky defects, same process once again, but you have to find the activation energies. The activation energy for gallium was 2.5 eV, and there's not many defects also. We only got 37.8 Schottky defects per centimeter cubed on gallium. The activation energy for arsenic was 2 eV, and this one had a lot more with 5.7 times 10 to the positive fifth Schottky defects per centimeter cubed.
Okay, next up we got diffusion length, which you can see from this equation here. We have our length is equal to the square root of d times t. Well, d is d naught times the exponential raised to e over a kb times t. D naught is the pre-exponential factor. Ea is the activation energy. Kb, Boltzmann constant, which is a number we've known forever, and temperature. So at 300 K, so I got a little cut off there. For copper, you have our equation here that we just talked about. D naught is 1 times 10 to the negative 6 meters squared per second. Ea, 1.2 eV, Boltzmann constant, in eV per Kelvin instead of how we usually see it. And then our temperature is 300 Kelvin. Put that in, you can, kind of self-explanatory, you can see how it comes out. D is 6.92 times 10 to the negative 27 meters per second squared. And finally, our diffusion length is 6.44 times 10 to the negative 13 meters. At 600 Kelvin, same thing, same process. And this time, our D is 6.92 times 10 to the negative 27 meters squared per second, which is actually the same, with a different diffusion length this time of 8.31 times 10 to the negative 7 meters. Same thing for gallium. At 300K, diffusion length, same equation, same Boltzmann constant, just different temperatures and values. So D, we get 8.63 times 10 to the negative 66 meters squared per second, and our length is 2.23 times 10 to the negative 32nd meters. And then over here is 600K, same exact thing, except this time our D is 9.12 times 10 to the negative 40 meters per second squared, and our length is 2.34 times 10 to the negative 19 meters.